We are going to actually do, okay, today we're going to do two things. We're going to do a recursive tree, basically see how the loop works. And we're also going to do, if we have time, we're going to do a subdivision, okay? These are already implemented as simple codes, actually, in JavaScript P5 website. But what I want to do is kind of do it from scratch with you guys and see how it works, okay? So a tree is basically a branching structure, right? So imagine we have a canvas. So let's say we have a rectangular canvas and we start with a single line. And what we want is this line to break into two lines. And we want to do this operation multiple times. And we want the branches to like keep branching. But what's happening is if we have a length for any type of generation, so imagine this is the first generation, this is second, this is third, this is fourth, fifth, and sixth. And the length of the lines are shrinking. And the angles are also kind of maybe reduced a bit, or maybe the angles are kept the same, right? So imagine we have an axis here. This is kind of an angle. So this is like an angle bisector. So we have a left and a right point to find, and we're going to draw two lines. And this is just a simple function. So it just takes a line and produces two lines. And we're going to do this in a loop, so recursively, and see how that works. Okay, so that's kind of the first exercise we're going to do today. Okay, so let's start with, I mean, first things first, we could actually do, I guess we could just draw the first line. How do we draw the first line? So we can specify a stroke to be 0, right? We want to draw, let's say, black, and stroke weight to be, let's say, 1. So let's start with the line. We want to start in the midpoint. So I can do line width divided by 2, height, and width divided by 2, height, minus 100. Right, so that's my first line. So basically, this location here is width divided by 2 and height, right? So this is W divided by 2. This is height. So we go all the way down, we go all the way right. So we find this point. And then width divided by 2, the x is the same, but height is reduced by 100. So the length here is 100. So that's our first line. Now, what I want to do is basically, after this, I want to draw 2 new lines, right? And I also want to think about this because we can do this in a bunch of ways. The first thing we can do is basically by calculating these points, right? The location of these points. And for that, we need to use vectors. So this defines the direction, and we're going to rotate the vectors. But I'm going to actually use translate and rotate operations to do this. If you remember, translate basically moves the construction plane to a new location. And then we can also use rotate to give this some sort of angle and then plot some geometry using that, right? So rather than using this, let's use it with transformation operations. So let's do translate. Where do I want to translate? I want to translate it to a new origin, which is basically width divided by 2 and height, right? So I want to move my origin from here all the way to here, where my drawing is going to start. And then I want to just draw the line at 0, 0. And I cannot use these anymore because I already translated my transformation. So what I do is just 0, and minus 100. Let's plot. So we are looking at the same thing, right? How did this happen? Basically, when you look at it here, let me actually increase my camera a bit. So basically what we are doing is translate moves us to a new origin, right? Which is here. And the X location right now here is 0, 0, right? It was here, 0, 0. This was my origin, but translate moved my origin to here with X is W divided by 2 and height, right? So that's the vector of transformation. So I moved my origin. And the second thing is the line is moved from the, drawn from the origin into this new point, which is X is 0 minus, Y is minus 100. So basically this location is 0 minus 100 according to the new origin, because the origin is facing this way, right? So this is the Y, this is the X. So if I do minus 100 for Y, I'm moving up in the direction because I'm going against the direction. Makes sense? So this is the new way of plotting this. So after doing this, though, what I can keep doing is I can use the transformation and I can plot the branches now. So what do I need to do? First, let me actually make this a bit larger. What do I need to do in order to plot the branches? The same way, we're going to draw lines, but we need to use translate and rotate. Where do I need to translate? Any, any idea? Where do I need to translate? So I want to draw these two lines now. I need to find this point.
Being also again give the 0.0 part for the translate. Yani, I mean 0,0'ın yerini değiştirmemiz lazım ki tekrar oradan bir başlangıç yapabilirim, değil mi?
Yeah, so basically my origin was here and then I translated to here, right? So this is, let's call this A and let's call this B. Now at line 9, my origin is at B. Now in order to draw the branches, I need my origin to be at C. So how do I get to C? What do I need to write? After drawing line, what do I need to write here to move my origin to C?
Again, translate.
I need to translate again, but what are my parameters for translate? How do I move from B to C?
100 plus 100 maybe.
So translate just takes X and Y. You just need two values, right? So I need to write translate here. And my X is going to be 0, but what is going to be my Y?
100.
Well, if I do 100, remember that my origin is facing like this, right? So this is Y, this is X. If I do 100, I'll move this origin outside of the canvas.
Well, plus 100 maybe.
Yeah, but plus 100 moves it here, outside of the canvas. I won't see it. I need to move it here. How do I get?
Excuse.
Yeah, minus 100. So I already have it here, actually. I already drew a line to it. So I just need to translate to my new origin. And then I'm going to draw a new line there, okay? And I'm going to make it into a different color so that you can see the second line. So I'm going to make it 255, 0, 0 into red, basically. Let's see, this one also changed. Why this? Because translate 0, -100. That's correct. Let me actually comment this out. Why is this? Oh, because it's constantly changing it. So let's make it here then. All right, because we are overriding the stroke value, so the first line gets another color as well. So this is what I wanted to achieve. So let's go over this. This is really important. Actually, let me make it -50. So we start here, background. We translate it to, we start from here, right? The origin is here, like this. This is Y, this is X. So I translate it to here. So this is B. Y is facing this way, X is facing this way, right? And then I draw a line in black, 100, -100. So this is the first line that I'm drawing. And then I'm doing a translate again. So at line 14, I move my origin to here at C. So this is C, this is B. And initially, when I create a canvas, my origin is at A, right? So that's how the grid is moving. And then at line 18, I'm drawing a new line in the red, 50 amount. So I find this point. So this is the new line. Make sense? So now let's rotate this and see what's going to happen. So if I do a rotate here, remember that rotate takes in, let's see, I think it takes in an angle. P5 library. Rotate. Let's look at rotate. So rotate takes in pi. Pi is basically radians, right? So angle mode, angles can be entered in either radians or degrees. I guess we can change the angle mode to be in degrees. So I just need to copy this. So let's go back here. Angle mode in degrees. So I'm going to rotate to -30. So let's see what's going to happen and where it's going to draw that line after translate, okay? Now it's rotated. Where did it rotate? So now what happened here at line 14, I moved my origin here to this point, but then I rotated in -30 degrees. So basically the Y direction was pointing in this way, but now it's pointing in this way, right? So now that's my grid. So this is 30 degrees, but it's basically rotated in the negative direction, in the clockwise direction. Makes sense? So now my origin and construction plane is rotated. So now when I plot in a line, this point is -50, like it's pointing in the opposite direction of my y-axis. All I'm doing is changing the plane of construction, manipulating the plane of construction, but plotting the same geometry. Make sense? So now I can also do this. So I rotated it, right? But I can also do it this way. So I can do push and pop. And I can do another push, but this time rotate it in the positive direction. Now what will happen? Now I get two lines. So why did I do push and pop? It's basically push, basically stores the current transformation matrix. It basically stores wherever my origin is at that location. And whatever I do inside here just is applied inside of this function, right? So basically at line 16, I'm storing this transformation matrix, and then I'm doing a rotation and plotting a line. And then when I pop, I go back to the initial transformation. So at line 16, my origin is like this, right? Then I rotate it, draw my line, and when I pop it, it goes back to the state again. So now I can rotate it in the other direction as well, right? So it stores that transformation. That's all the push and pop does. So if I don't do this, what will happen is, like, let's actually try. If I don't write these, let's try what will happen. It will look like this. Why? Because I rotated the transformation in negative 30 degrees. Now I'm rotating it back to 30 degrees. So it's basically aligning it back to the original condition, right? So I'm rotating it back to its initial state. But I wanted to do this as kind of a symmetrical branching. So that's why I'm incorporating push and pop. Okay, so that we get an angle bisector. So I want to have these angles to be the same. So if I do rotate in the negative degrees, I draw this line on the left, but then when I pop it, I go back to here, and then I do a right rotation. So I draw this line. So this will be positive 30 degrees. This is positive, this is negative. So the reason why I'm doing it this way is so that we can actually make this recursively, right? How can we make this recursively? So let's say I want to draw 5 branches along the way, like 5 generations of branches. How do we do that? So basically imagine that we want to keep branching like this. So we need to keep track of transformation matrices. So we need to move along with the branches, right? So one thing I can do is maybe do this once. So I'm going to put this inside draw. So we just plot this once, and we don't draw it constantly, but then I'm going to make it more parametric so that we can enjoy it. So basically, first things first, we need to define kind of a loop here, right? And we are doing kind of a translation as well. So imagine that we want to create 2 generations or 3 generations of branches. Then we need to do this recursively, right? So how are we going to do this recursively? Any idea?
In the reference, we have some step by step to solve and automatically give the lines maybe.
Yeah, so what I want to do is basically make this automated, right? So I'm starting with a single line. And then when I get this line, I just want to draw 2 lines. And then I want to move to this point and then move to this point and keep drawing lines, right? That's all I want to do. So the first line, I think, will be drawn, but the branches, they need to be in a function. They need to be plotted inside of a function. So this part, basically, including translate as well, I think, it could be recursively done inside of a function. So how can we do it?
Falan orayı alıp fonksiyon içine yapıştırsak yeterli olur mu?
Well, we could, but keep in mind that we are generating a tree, right? So we start, every time we are branching, we are here at this location, and we plot 2 branches. And next time, I want to move here and then plot 2 branches. And I want to move here and plot 2 branches, right? So I need a way of tracking the transformation every time, and I need to use it for new rotations and new branches. So this function basically needs to be inside of a loop, inside of a recursion. So it needs to basically have a callback. So what we could do is like this part up until here, this is the trunk of the tree. So this could stay where it is. We don't need to change this. So we can start with a new origin, start with this line, and translate it here. After this, we know we're going to have two branches, and then we know we need to have a loop. So let's write it into a function, shall we? Let's call this as a branch, okay? So what branch does is basically, essentially, would it work that way? Let's brainstorm a bit. If we do this with translate and push, so I want to move, like every time for every generation, I want to move to this origin, like the translate would actually be the branch itself. Then I want to plot
Ya içlerine crunchy koymamız mı gerekiyor? Yani push ve pop'un arasına bu crunchy'ye yerleştirmemiz gerekiyor ayrıca.
evet. Yes, like we need to basically have this as a recursive function, right? So every time we have a line, we want to move to the end of that line and create a new branch, and then move to end of the branches and then branch again, move to the end of the branches and branch again, right? So that's basically where the recursion is going to happen. So we need to automate this in a way and keep track of the number of generations so that we can also stop it. Make sense? So let's do this for just one side. Okay, let's assume that we're going to do it for the left side. All right. So how can we do it? Basically, if let's say we define a generation. Let's call it gen. Let gen equals 5. So initially our generation is going to be 0. Okay. So while gen is less than is greater than 0, and inside I can do gen minus equals 1, which means gen equals gen minus 1. It's exactly the same thing. Gen minus equals 1 means gen equals gen minus 1. So I'm decreasing gen by 1. And let's make this 2 actually. So we're going to have a while loop here. It's going to terminate. So it's going to start at 2. So is gen greater than 2? Yes. So we're going to be inside of here. When it hits line 15, it's going to be reduced by 1. So it's going to go back to line 12. Gen is 1. Is 1 greater than 0? Yes. So we're going to be inside. Gen will be reduced by 1. Gen is 0. Is 0 greater than 0? No. So we're not going to enter here, and that will be the function, right? Inside of this, what I want to do is do the translate operations. So how do we do that? So let's do it this way. So let's do translate here. So I move to the end of the line. And then let's do the push and pop here. Let's see if that would work. Would this actually work if I do push and pop? So I do rotate minus 30 stroke, and then translate 0 minus 50. Let's see what's going to happen. So what happened? So now basically I'm recursively translating and rotating now, right? So if I make this 3 or 5, I'll basically keep rotating and translating. Make sense? I just moved to this endpoint, rotated negative 30, draw the line, translated myself there, then went back, rotated negative 30, translated, rotated negative 30, translated, rotated negative 30, translated. I did this 5 times. And every time I'm doing it, I drew a red line. Make sense? That's how I got this. Basically, one single branch. Now, what I can do inside of here, I can basically, I did this recursively. But I also need to do this to the other side as well. How do I do it to the other side?
Is there any
Okay.
command like mirror?
Well, we don't have to do mirror. We have the rotate, right? I can also rotate in the other direction. So technically speaking, before I translate, I can also do this. I can do rotate negative 30,
160.
but I can also do rotate, rotate. Now I have to do 60 maybe. And do this. Now this happened. Why did this happen? So what's going on is let's actually walk through the code. So I'm at line 16. So I'm rotating negative 30. So I'm drawing this line. And then I'm rotating plus 60, right? So I'm rotating it back here and I'm drawing this line here. Now, when I do translate, I'm translating it to this point. And then I'm doing rotate negative 30. So I'm drawing this line. And then I'm moving back 60. So I'm drawing this line and rotate, translating it here, right? I'm not actually storing the transformation matrix every time. I'm doing this. So that's kind of the issue. So we need something else here, actually. So the reason why we need push and pop is basically we need to store the transformation matrices. Because otherwise, if we do this in a single while loop, we're not going to branch in every like this code has to recursively increase the amount of branches it plots for every generation. So how do we do it? Let's think. So every time I'm here, I'm going to do translate, draw a line and branch, draw a line and branch, and then I need to submit it to some other function. Well, we need to also do push and pop. So what if I have a function called branch, for instance, that I take just the point, the origin, and then I call a function called branch. So let's write a function. Function branch. It's your first function. So what it does is it just basically plots two new branches, right? That's all it does. So let's define this actually. Rather than doing this here, let's call this function here, branch. And we already know the origin. We're just going to branch at the origin. Okay, and I just copy this, put it here. And I just call my function. Let's see what's going to happen. It's probably going to do the same thing. Yeah, it does the same thing, exactly the same thing. So now I converted this routine into a function called branch. Okay. I'm also doing it here, by the way. Let me actually hide that. It was just adding one more generation. So what branch does is exactly this. But what if now I actually stored the transformation matrices, and I call this only once. Okay, so let's do it this way. So let's do branch, and let's do branch gen. Let's keep track of the generation inside of this branch. Let's call it. Let's make this into a parameter. So and I can do if g is greater than 0, do this. Okay. So I'm calling branch with 5, didn't need to have this parameter, but let's call it with 5. If 5 is greater than 0, just plot one variation like this, okay? So what's going to happen is probably it's going to just branch once, right? But now this allows me to do something very interesting, because now I have a function and I have it tied to a variable. I can actually do this recursively. I can have a callback. I can recall this function automatically. So basically what I can do is inside of this function, every time I'm entering here, I can have, I can call branch again, call itself again, okay? And I can do this after I do the rotation and translation. So let me show you how this would work. I'm going to delete the rotate, and I'm going to delete the right branch. And what I can do here is write push and pop. So I can store current transformation matrix and run this. So I'm only plotting the left branch, okay? But every time I'm doing this, after the translation, I want to branch again, right? So I want to keep doing this operation. So if I do branch, let's do branch, and after we move here, that's true. And I want to do G minus 1, reduce G, because this will now call itself. So keep in mind, we need to stop it from calling itself, right? So rather than writing it as a while loop, now I'm doing it inside the function. So this function is calling itself. So this is recursion basically. So imagine something that calls itself back and forth, right? If I call itself the same way, if I call it with branch G, this will create an infinite loop. Make sense? Because we are not reducing this condition. So this function will, regardless, like enter inside here and call itself back and again. So it's all, G is always going to be greater than 0. It's not going to stop. So it will basically crash because it cannot call itself back infinitesimally, right? So I need to create a condition. That condition is this if statement here. So I want to create a condition where I'm reducing G so that at some point, G wouldn't be greater than 0. So it won't enter into this callback. So it won't enter into line 27 and call itself again. Make sense? And why am I doing it here? Is because I want to keep track of the transformation matrix by push and pop. But every time I'm drawing a new line, I want to translate to the end of that line and call branch again. So I want to branch at the end of this line again. Okay? So now if I run this, now I can actually do this operation recursively. The same thing that I wrote inside the while loop. Now I'm doing it with a loop, like with recursive call. I'm going to stop here because you need to understand what's happening. Like you need to wrap your head around the concept here so that we can plot the tree now. Let me actually show you something more interesting. So let's imagine this parameter to be something else. Okay, imagine that we are plotting a line at some length. This length could be a parameter. Let's make it into 100. So I'm translating, or let's call it length. Okay, so let length equals 100. So that's like the length of my first branch. Okay, so I'm going to plot my line here at negative length, and then I want to translate that amount. Now, this is a parameter that I can use in my function, and I can take it here. So let's call it L. I can also call it length, by the way. Like I can have the same name, but this is not a global variable. It's a local function call. So whatever I'm giving to the function, I can take it with a different type of name here. Okay, so that's the name of my function. So I'm defining a function called branch. It has two input parameters, and one of them is gen, the other one is length. So these are going to be assigned a number. So I can now take this in and I can do length times 0.9. Okay, so I start with 100, but the second generation is going to be 90. And then I'm going to pass this back to the function, and it's going to multiply by 0.9, so it's going to be 81. Make sense? So I'm going to always plot 90% of my length threshold. So it's going to recursively decrease in length as well. So I can put it here too. So let's see what's going to happen now. Let's see length. This should be fine. Maybe we need to give it a different name. Let's try. I don't think this would be a problem, but line, this is fine. Translate, we are moving there too. This is exactly the same. Why didn't this work? Branch length. What was the initial condition? So this was the initial condition, right? Yes. So minus 50 and 50. So that's minus 50. Okay. Oh, I see what's going on. So what happened? Why didn't it work? Can somebody point out why it didn't work when I run this? Why it stayed like this? Look at line 30. Can somebody point out the problem?
Virgül mü koymamız gerekiyordu?
Well, we are calling the function with two variables now, right? Number of generations and the length of the branch. Make sense? So I'm calling it here, I'm giving it a length, which is initially 100, and I'm drawing 90% of it, and then I'm translating 90% of it. But I'm not passing this back to the function, right? So I need to include this in my new length. So if I pass this in, that means I'm also decreasing the length every time for every generation. Now you can see it's going down 90% at a time, right? So this is 100, this is 90, this is 80, this is 70, sort of. So we don't have to start with 100, and we don't have to draw 90% of it. We can just draw 75% of it. Right? Now, this is 75. This is 75% of 75. This is 75% of 75% of 75%. Okay, like that's big. I can also plot the length of each line if you want. For instance, I can do print length times 0.75. Let's look at the lengths. So initially it becomes 75, but then it becomes 56, 42, 31, 23, right? So it's recursively decreasing in length. Make sense? So I'm now I'm showing you every generation where this operation takes place. So push and pop basically stores the current transformation matrix, but because I'm calling my recursive function inside of those, I'm always moving to the new origin and then branching there. And when I'm branching there, I'm moving into a new location and then branching there again. And then I'm moving into a new location and branching there again, right? I do this 5 times. I can actually do this a lot of times because it's parametric. So now I can do this 3 times. I can do this twice. I can do this 6 times. Let's do it 20 times. Now it's a spiral. Make sense? Every time for every generation, I'm moving 75% of the amount and I'm rotating. Now
Tamam, bir şey yapabilir miyim?
Yeah.
Ben bu branch ve length komutunun anlayamadım. İşlevini tam olarak. Yani mesela Can yerine neden i kullanmadık? Hani while kısmındaki mesela o çok anlayamadım. Bir branch kısmını anlayamadım.
Okay, so we are trying to do recursion. Okay, recursion is basically a function that calls itself. All right. So every time, the first time I'm calling branch, all I'm doing is I'm calling branch here, right? I'm calling branch here. I'm basically translated to this origin and I called branch. That means basically create a branch. That's what the function does. It creates a branch in the positive direction right now, only towards left. We haven't done it twice. So inside of branch, something interesting happens because inside of it, what I do is I'm checking the generation. So initially we start at 20, so it's greater than 0, okay? And then I'm doing a push and pop. The push and pop functions, basically it stores the current transformation matrix. So every time I do push, I basically push to the stack the current transformation matrix. So basically I'm storing this location and the current alignment of the transformation matrix, right? So I'm storing this. Okay. And then inside of it, I'm doing a rotate and a translate. So I find this point basically, and I'm drawing this branch. And then I call branch again. So what happens is I already moved here. And then I'm calling branch again before I pop the transformation. So I'm here and I call branch again. So I'm going to do the same stuff. And I keep doing this 20 times. And then I pop. So then I get out of the function, the transformation, okay? The reason why I'm doing it this way is because I want to store the location of each branch. Because then I can do a branch in the other direction as well. Okay, that's the whole reason why the function call is inside of the branch. So it's a function that calls itself. We are trying to store the current transformations. So imagine this, like I'm starting here and my function does a rotation and a translation. So it moves here and I want to store this point as well, right? But before I come out of that transformation, I branch again. So I keep doing this again. I keep doing that again a bunch of times. And then this is going to pop. So I can also do it this way, by the way. Let's do print G minus 1. So you can see how the end of, so look. So the first things that are plotted are the lengths, but then my gens are plotted. So it starts with 0 and then has a backtrack. It starts at 0, basically it pops the end of the stack and then it goes back in the direction, right? It's a concept of basically how the algorithm works. So it's a function that calls itself, but because we are plotting a tree, we need to also translate and rotate the transformation matrix. I can do this in a linear way as well, so that maybe the rotation might be confusing you, but I wanted to do it this way so that you can actually see the effect of this algorithm. Okay, so if I, for instance, write branch here, what will happen? You want to see? I hope this won't break, but let's call this recursive tree. Now this happens. Basically, every time I push the new transformation matrix, I branch after I pop it. So technically speaking, my branches are plotted in the same origin because I'm popping the transformation matrix, right? So you can see that there are tons of lines overlapping at the base. So basically it's plotting the first line, it's plotting the second line, third line, fourth line, fifth line, sixth line. So it's plotting it at the same origin with the same transformation rather than adding them on top of each other. Makes sense? Because pop basically takes it out of the stack. So rather than moving and storing this location, I'm moving back to my initial location if I do a pop. So push and pop basically help us keep track of how we translate and rotate the current transformation matrix. It might be a bit confusing. Maybe I'm not explaining it as clearly, but the reason why we need to do this recursive call inside the push and pop is for us to be able to keep track of the branch. Right? So the other part of it is pretty straightforward, actually. You can see that we did a rotate -30, and then we did a translate. So all I have to do now is basically I need to write branch here again. But I also need to keep track of the positive and negative direction. So I only did one side. I also need to do the other side, right? So inside of this, I need to rotate to the other side as well. So maybe we do it this way. So maybe we do, maybe we do angle. So branch, let's call it 30. And then I do -30. And then I pass in angle. I'm wondering though, maybe we don't need to pass this in. Because it's consistent. This would work if I define a variable, global variable here. But I need to keep track of the side of the branch, like if it's left or right. So I'm doing it in the negative direction. So maybe we do it in this, like a parameter called side. So I want to do it -1. And this is basically angle is 30, and I multiply 30 with side. Side times 30. And I need to pass this in here, side. So I'm exactly doing the same thing, but now I want to do it once. So negative side, and I want to do it a second time. But this time I want to do it in the positive direction. Right. And now I want to do it here too. So I want to do it double, and this is negative side. And let's make it into 2. Voila. So let's see what's going on here. Let's comment this out. So now what I'm doing is I moved to this origin and I'm calling left branch, right? I'm moving in this direction. Let's call it branch. Maybe we could even do it, actually, we might not have to do it twice, but maybe once, because inside of this, it's already calling it back itself. But let's keep it the way it is right now so that we can understand what's going on. So I keep track of generation. I use length as a diminishing length. And now I include something called the side. So I want to do it on the left side and the right side, right? And that's controlling the rotation. So remember that side, if it's -1, it's rotating towards left. If it's positive, it's rotating towards right. So in the beginning, I'm in this location. I call branch in the negative side. So I call this function basically. And what do? I rotate left, translate, draw a line, and then call branch twice because I'm at this point and I want to branch in 2 directions again, right? So I want to branch in the positive side and the negative side, but I already rotated left. So I want to take in this transformation in this location as well. The reason why we do it this way is because now I can keep track of every branch, and I can branch in 2 directions at every branch. Okay, now let's make this into 10. Now it does it recursively. So basically, we are branching at every location. We are branching double, and we are branching on the positive side and the negative side, and we are keeping track of the sides as well, because I'm taking this as an input and I'm using it for my rotation. Okay, there are probably easier ways of writing this as well, but this is basically a function that calls itself, and with push and pop, it keeps track of the current transformations. So I can also change the angle. Maybe I can use it as a, not as a side, but as an angle parameter, and decrease the angle with certain thresholds. So these can maybe start at 30 degrees and then rotate at a lower angle. But I want to stop here and see. I'm pretty sure you have some questions, but let's actually hear them first. And I'm going to take these out. So that's kind of the tree that we have. So look at the function. The push and pop, again, it just stores our transformations, right? And the reason why I'm calling branch inside of it is because I want to keep transforming the branch. So the first thing that it draws is actually the further left branch. But because I'm calling the other side as well, it also starts plotting these lines and then keeps tracking these additional branches here as well at every generation. Okay. What we could do is actually maybe increase this a bit. So for instance, we have a stroke weight function. Maybe we want to make the trunks go lower in size. Let's see what we could do. Oh, I can also do it something else. Basically, I could also do, rather than calling it like this, I can call it only once, actually. And draw 2 lines. Shall I do it that way too? Move to the end. Well, there's another way of writing this, which is probably a lot simpler. Basically, we want to keep track of the transformations, and then when we don't transform, we can plot the lines. But I'm going to keep it this way. This is like one way of writing this function. Let's actually play around with this a bit. Let's decrease the angles over time. So let's call it, and we define the length parameter. Let's call it an angle parameter. Let angle equals 30. Now I'm going to give this as an angle. So minus angle and plus angle. So now this is a parameter called A. So I want to do it not side, but A. And this is A and minus A. It will work the same way. Now I can do this. I can multiply it with 90% when I'm calling branch. So the top branches will actually lower the angle as it's growing. And I can also do something pretty cool, actually. Basically, I can make this interactive if you want. Shall we do it interactive? Would you like to see it interactive? Like with my mouse, like when I move my mouse, it basically changes angle or length. Yes, let's do it interactive. So we could actually do, rather than calling it branch here, I can actually do branch called here. Okay, but I'll probably have to do all of this here too. Yes, so now it's plotting this every time on the canvas. But now I want to have the angle or the length even to be influenced by my mouse, let's say mouse X or mouse Y. Okay, so we can have a function called map. So let's look at map. Map basically takes in a variable. Let's call that variable. Like here, the value is 25. So we're going to create something like this. Basically, you can see that my mouse interacts with the way some value is mapped. So what it does is it takes in an interval of, let's say, the X location is my input, right? I'm using mouse X is my input. And the X input could be between 0 and width, right? So it will basically be between my canvas, but I want to map it to 25 and 75, right? So whatever that value is between 0 and width, I want to remap it to 25 and 75, okay? So when it's 0, I'm going to return a value of 25. When it's width, I'm going to return a value of 75. And when it's in between, it's going to be 50. Make sense? So we can actually do it for our length parameter. For instance, if I do map mouse X, so what can the value of my mouse X could be? It could be between 0 and 400. So I can do 0 and width as my input. And the length, I want it to be mapped between 10 and 100. So when I'm at 100, when I'm at width with my mouse, I want this tree to be longest. And when I'm closer to 0, I want it to be shortest. So now it's just scaling up with my mouse, right? So when I'm at 0, length is like 10, really short. When I'm moving all the way to width, it's becoming 100, right? So it's taking an input with my mouse cursor. I'm going to do something similar with angle. So I'm going to do map, but this time I'm going to do it mouse Y, 0 height. And I want my angle to be 0 and 30. Well, let's make this 2 degrees, really, really small. So it's going to like blossom out. Right, so now when I'm at 0, the angle is really small. So it starts at 2 degrees. And when I move down, the angle gets to 30, right? So now this is both scaling up and opening up, right? I can do this because I'm using, I'm changing the length and angle parameters interactively with my mouse, but I'm also translating the parameters on the canvas. I'm wondering if we could also do something else. Maybe we could also map maybe the reduction of the branches. For instance, the 75, well, how much we basically reduce the length, right? So this parameter might be another variable that we want to control. And let me actually show you, we can define this as a global variable. So for instance, let's call it let r equals 0.75. So now this is a variable that I'm defining outside of my function calls. So this could be accessed by every function. And I'm going to use this r here. So it will be fixed as a coefficient. So now this works the same way. But now I can also control it. So I can do r equals map. Let's make it interactive with mouse. So it's between 0 and 1, right? So mouse, though, is between, mouse X is between 0 and width. And I want it to be mapped between 0, let's say 0 0.2 to 0 0.8. Let's see what's going to look like. So now it's also growing. Pretty cool, no? So now when I move my mouse, it's both the reduction is the rate of growth is also increasing, and the length is also increasing. So now they're complementing each other. And my Y location controls the angle. So if I move diagonally, it will, or move it horizontally, or let's move it. Yeah, if I move it from the origin, 0, 0 to all the way to width and height, that will be the basically mapping of my growth sequence. Make sense? Shall we add one more step to this? I can also randomize the tree. But I'm not gonna do it. I'll let you guys figure it out. Or shall I do it? It's pretty straightforward, actually. What you need to do is have a fixed random seed. So basically, every time we start the function, we want to call it random seed. We want to have the seed to be fixed. Otherwise, it's going to have like a lot of flickering. And then I want to multiply random the lengths with random. That should be it. Oh, it's flickering already. Why? Something's not working right. Shall we do it? Oh, we have to do it every time when we call draw, probably. So here. Oh, but it's only doing it for the first branch. It's not doing it for subsequent branches. So let's do it actually here too. Ooh. Now this is fixed, of course. So you have to do it. Well, the lengths are diminishing too much. So maybe we do it 0 0.7, 0 0.7 and 1. So we give it some interval. Right? So every time I run this now, we will have a random tree. Is this the same? No, it's always the it's always with the seed 0. In order to get a different tree, I need to change the random seed. So the seed controls the type of tree we are generating. And I will add one more thing with the stroke weight. So we are drawing with the stroke weight. We could actually do, let's make this, shall we reduce it every time? Let's make it into a function as well. So let SW equals 5. So that will be our stroke weight. So we start with the stroke weight, but it will reduce every time itself, right? So would it be fixed? Well, we have to pass this in as well, probably. We can also use it as a mapping function. For instance, we have a variable called gen, right? So gen starts from, what does it start from? It starts from 10. So the maximum is 10. And the minimum, it's going to be 0. So I can use it for my stroke weight as well. So for instance, I'm drawing a line here. So we can start with 5. And here I can do another stroke weight. And I can do a function called map. Map gen. We're going to map gen between 0 and 10. And I want my stroke weight to be 0.1 to 5. So when it's 10th generation, it's going to be thickest. So we need to reverse this. This is a bit more advanced. What happened? Gen instead of get. Oh, G. This has to be G. Sorry. Oh, why this? Well, the line weights are not plotted correctly, so this has to be the other way probably. So we need 0.1 and 5. Yeah, now they're thinning out. Well, 5 is a bit thick, but they're thinning out, right? So every generation, we are mapping in a new thickness for the line weight. So when we get to the ends of the line, ends of the branches, it's getting thinner and thinner. So I did this with the stroke weight. Yeah. Nice little tree. You must have a lot of questions. Let's hear them. Was this too difficult, too advanced? Huh? But it's pretty cool, no? Let's plot a new tree. I want to do it, let seed equals 20. I want to assign the seed every time I run the function, and I want to pass it in here. So every time I run now, I get a new different tree. These should be different, right? So this is 1. Are they the same? No, they're not. Yeah, they're different. Let's let's make some of the lengths long. Shall we do it longer? Can they be longer? So here, for instance, we are doing 7. Let's make this 1.2. 1.2. Yes, some of them are now longer. You can see it's not like a correct way of how growth works, right? So they have to be hierarchically shrinking in length. Let's make this 5, this to be 8. So I'm going to just make this asymmetrical so that one side is shorter than the other side. All right. This was actually in the editor file as well. So if you go here to reference, there should be a tree here, if I'm not mistaken. Where is it? There should be examples. Shape. Am I missing something? Let's see. Well, maybe examples. There we are. Examples and structure recursion. Recursive tree. It's doing exactly the same thing, right? So it defined a function called branch. it's doing the push and pop twice inside, but it has the same kind of workflow. It's calling branch once, but every time it calls branch, it's doing push and pop twice. I could have done it this way too, but I kind of made it into a double call, and it's outputting the same stuff. You can see. So it's mapping the angle to be horizontal. I mean, to 90 degrees, between 90 degrees and where is it? Angle is mouse x divided by width times 90. We can also use this. Where's our angle? Angle mode degrees, branch. Angle is map mouse y. So we could do mouse y divided by height times 90. Wow. Well, ours is asymmetrical, so that's why it's already doing a lot of cool stuff. But if I make it to be exactly symmetrical, then I have to get rid of the random function. Okay, what do you guys think?
Teacher, can we change the color of each line? Can we give random colors also?
Absolutely.
Stroke one.
Absolutely, we can. So we are doing stroke 0. We are not changing the stroke. So let's make this into a color gradient. Okay, shall we look into that? How to make it into a color gradient?
Shall we?
Yeah, we can definitely do it. So look at how I'm doing the stroke weight. So I define it as a starting value, right? And I am basically mapping it. So just like that way we could also do lerp color. So lerp color basically interpolates between two colors. Okay, and I use this, like this is basically a coefficient. Like when it's 0, it uses color A. When it's 1, it uses color B, and it interpolates between them. So we could define two colors, like from and to. That's called, I mean, from could be black, to could be white. And let's make the background to be red. Let's do this color A. Let's do this color B. I guess we have to define these here. Color A equals color 0. This is black. Color B equals color 255. This is white. And we can define these as two variables. Okay. And now I'm doing it on a red canvas. But the reason for that is because I want to make it visible. Let's make this a bit. All right. So stroke weight is SW, and we have a stroke value here. So what I want to do is assign the stroke to gen as well. So rather than using this, I want to do stroke here, define a new stroke value, and do lerp color. We want to do from color A to color B. And we want to use the third value to be this map value. So I can also do map. Yeah, we could just, I have to put it in here actually. So we want to map G between 0 and 10 to 0 and 1. So I'm basically normalizing G. I can also do G divided by 10, by the way. G divided by gen. But then we could do gen here as a global variable. So I can use it here. So this will normalize it, right? When gen is 10, it will be, this will become 1. But when gen is 5, this will become 0.5, so midpoint. So color A is black, color B is white. So that will, yeah, so it's going from white to black. So what we need to do is probably color B to color A. Yeah. Right, so we start with black and with white. But technically speaking, we can define any color we want. So if you want to lerp between, let's say, black to, let's also use color A to be our first color of stroke. Shall we go from red to green? We can do red to green. RGB. Red to green.
Böyle üstlerine böyle yaprak kesimi veya böyle şey ekleyebilir miyiz kenarlarına? Belli bir seviyeden sonrasında. Böyle bir komutlandırma yapabiliyor muyuz?
You can draw any shape you want because we are using a transformation matrix, right? So I'm just drawing a line right now. But if you want to draw a more complex shape, you already have the current transformation matrix here. So rather than just drawing a line, you can draw any type of shape. You can draw a rectangle even. I can do a rect 0, 0. But what shall we do for the rectangle value? Rect. Rect mode. Corner, center. Shall we do center? Center, radius. Well, the problem is we need to, well, we have to probably translate it to the middle of the rectangle as well. So if I do the rect mode center, rect mode center. So now rather than drawing lines, we can do rectangles, right? So rect 0, 0, but I also need to do translate by half. So with
We need to form location, right? Like 0.0.
yeah, so I need to translate it by half of my y and do another half here. And then use this probably, let's see, length times r divided by 2. I did this a bit fast, but let's see. Yeah. So now we have rectangles.
Okay.
Makes sense?
Yes.
So this is probably more clear to see because you can see that we are controlling. I'm not doing it in the first branch though. The first branch is just a single line. So I need to also put, rather than the line here, I need to put the rectangle too, right? So I can do, for instance, translate by half here because we are using rectangle mode to be at center. So I'm moving half translation, plotting plotting length divided by 2 and length. We have a rectangular tree. Okay. This was like, this got out of hand a bit, but I think when you study this, you should be able to learn both recursion and translation and rotation as well, right? So you can see that we are translating and rotating the construction matrix so that whatever geometry we put on it, it will have this type of look. One advanced version of this would be to actually keep track of, let's say, some value for the branch thickness, right? Because you can actually do like a trunk Let's actually make this kind of tapering. Like it will be better to draw this almost like trapezoids, out of trapezoids like this, so that your subsequent branches would get actually thinner and thinner. Make sense? So you need to keep track of two values. You need to keep track of this width, W1 and W2. And you need to find these vertices now, because you cannot draw this with rect command. You need to input these vertices. But because we have an axis and a width, you should be able to plot these points and draw it with begin shape and end shape. Make sense? Maybe we will do this later. I mean, if you want to see it, it will take some more time, but I'm just going to leave this here so that you can play around with this code. Maybe we could also do, oh, we are doing stroke only. We are not doing fill. Let's actually do the other way. So let's do fill and no stroke. I'm going to do no stroke. Right. So because it's not trapezoidal, like the trunks are not continuous, because I'm drawing a rectangle there. Makes sense? The shapes are kind of breaking up. But if I do it with an angle, they kind of overlap. But we need some sort of an angle to actually hide it. Like here, it's kind of visible. Let's make the colors a bit more interesting. Background, let's make it black. Shall we do it tones of blue? Cyan is...
Can we take a break, by the way?
Huh?
Can we take a break?
Yeah, I'm going to end it here, actually. Do you have any questions? Shall we continue with new exercises, or shall we stop here?